Hello, today I'm going to try to derive the Einstein field equations. This will be a basic introduction. It won't be rigorous.
My balls.
It will cover
you know
the
what?
essence,
This is a slaughter
but it will still
factory
be
right here,
quite
man.
complex.
Mathematician.
If you want more detail, then I refer you to Professor Leonard Susskind's excellent lectures that he gave from October to December 2008 at Stanford. I've put a link to the YouTube version of these lectures in an annotation on this video. I am going to follow his approach so that it will be familiar to you, but I shall do it in a much more simplified version.
I'm going to do it much more simplified than that. This is a black hole, singularities are a chess game. We're going to talk about that chess game a lot, about those vector positions that come up to your time dilation systems of chemistry, decay, fusion, Murphy up here playing Mario on vector positions, and that being some superposition states of you being in a box, in
particular, that you're aware of two key points. The first is what is called the principle of equivalence. And what that says is that if you are in a box with no windows, then you cannot tell the difference between being in outer space and accelerating with an acceleration g,
but it does.
Or being in
mathematically in the chess game, are you upside down pineapple cake for middle phase on the board of the stone metal? That's why I brought this one specifically. Because as soon as you have a given value, this stops being an element or a cap or the standard model matrix of what you know inside a G for any gray alien civilization or otherwise. You want to stop caring, you don't have the equipment, you better go.
If you're in outer space, traveling with an acceleration g, then all parts of this box, including you, are accelerating at the acceleration g.
Later about.
If you are on Earth, then because the value of g varies according to the height above the Earth, the value of g at this point will be ever so slightly greater than the value of g at this point. And so there is a slight difference in the value of g in this situation.
I believe that you're American, they can say the First Amendment was you being a laborer, a mason, a manager, a plumber, Mario, or a mathematician.
That, Einstein said that that was a principle of equivalence.
Now you bring me my marshmallow
right now. You can't tell the difference whether you are accelerating at g or subject to a gravitational force, which is represented by the acceleration g.
That's a good one.
The second principle is that light
This is what happens when you let the crew get involved with the safety video for skid steers. And they come out with this.
The person who is in the box that is accelerating through space with an acceleration g, and here is
one of these brothers, one of those brothers, standard model.
And this time we're going to shine a light from this side of the box to the other side of the box.
So you don't know if you're falling.
But of course that will take a finite time, albeit small. And if this box is accelerating with an acceleration g, by the time the light gets halfway across, the box will have accelerated.
Certain decay states are different between helium and hydrogen.
Forward. So it'll now be here,
what states
the light
they are in the machine.
There.
Like, you know chemistry, because chemistry is a pretty freaking easy machine. It has human limitations on timelines that are sensible to X, Y, and Z, different forms of what causes a collapse, what lenses a problem. They have multi-values against, again, Einstein, or whose ever standard model this is. Now, he's just explaining any field. You're in a field, on fields, which we'll get into the important topic here in a moment. Says Carl Sagan universe loaf. I don't know whether I'm up, I don't know whether I'm down, I don't know if I'm upside down.
So Einstein says, if that is what happens when you are accelerating,
I'm in a field, that sucks. But now you can be in a field squared.
Since the principle of equivalence
I know how fucked I am.
You can't tell the difference between that and being
you're never sure about that, because a singular anomaly could come crashing in here about being in a box upside down. Didn't know.
In this scenario here, that light will appear to bend.
You could say the neutrinos. There's a curved space.
Now, of course, he could
45 is great on the stone mill floor.
But in fact, this was shown to be
and
true.
then we use this field theory.
During a solar eclipse.
Which one of those keep it on a straight line inside this pipe? So I knew this was fusion speeds cut window. You had to walk this, which is a tilted angle of the floor. It masses out. This is going to be the screw bowl.
And what was noted from the position on Earth was that they could see a star
I watched it get a little
to the right of the sun.
And I knew it early.
But they knew, astronomers knew, that that star actually was located behind
maintenance
the sun.
Rotations on monthly, weekly, bi-weekly.
And the explanation was that what was actually happening was that light from that star was being bent in the gravitational field of the sun,
the Sophie star over here, putting up some stuff about the Dyson Bell I'm trying to do.
Giving the impression that the star was here, when in fact the star was really here, but the light was being bent in the sun's gravitational field.
So those maintenance reports, you know what I'm talking about? And you take the angles out and you do the schematics a little different.
Law of gravitation, which everybody had
FMA every day, Brother Poncure out here is going to hit you with this form of it in both. Watch this. And you missed that number.
Times the mass of one body,
Jupiter's going to be pissed.
Mass of another
back to that first question. How do you know you're on Earth? Because I do this and it does 9.8 meters per second squared. And if I did it too much, Jupiter's going to get pissed at me. You might not think about it, but given the numbers that lens, alright,
here, light is bending
that would mess stuff up.
Field, but photons of light have no mass.
You roll
so
for
these
graph.
two mass terms, well, at least the sun has mass, but the photon doesn't. So this form of Newton's law doesn't work.
Well, if the comes down later and Einstein's like, are you going to take this paddle right now? Because I'll give it to you, buddy.
So Einstein came up with a completely different approach to gravity. Instead of there being gravity, he said, actually what is happening is that all forms of motion are represented by movement in curved space-time.
I can get work out of that.
And I can illustrate that in this way. Let's suppose that we take a trampoline.
Happens fast.
This is the surface of the trampoline. And that's representing space-time.
There's going to be a field.
We put a small marble on that trampoline. The marble will have virtually no effect. It might make a very tiny indentation on the trampoline.
It's a really flat hill.
But now let's suppose I get on the trampoline. But if I get on the trampoline, with my weight, the trampoline is going to bend.
I was
quite substantially.
unloading the saw. Normal day against how it affected a thing.
Space-time, or curved space-time.
Here was
our
product.
What's going to happen to this marble? Well, the marble is now going to fall.
If I slice this off into a penrow, you're right. You're right. I can't quantify those things. They're still on that somewhere in here. But if I track this damn rat.
Now, Newton said that movement towards me.
You're gonna be white feather in the ditch, hiding on land nav inside of here. White feather trying to get away with shit. I know. It's how you dodge bullets. You can't. They don't do that in this timeline.
Along the shortest path in curved space-time. So that when the Earth goes round the Sun, there's the Sun, and here's the Earth in a reasonable circular orbit.
This could be the rock over Augustine. So this is what
Newton says
here,
that there's a
gravitational pile of rock up on this side, a pile of rock up on this side. Here's the pile of rock with all the veneers inside of it. And this could be a loop. It could be. You could be actually in a ditch on the far side inside of here. But what I do know is you'll have to get past this because the veneers are back here. And then the back of the wall is outside here. What your mission is to get inside here. Come in here, white feather. Just go through all this rock.
Now you might be wondering two things. Firstly,
jump
what
up in
is
that hill
space-time? And secondly, why did Einstein think
no
that
reason
it would
for you to
be
be
curved? Well, space-time is really just space and time, all thought of as one set of coordinates. We usually think of space as having three dimensions, which we represent by three what are called orthogonal axes. They are at right angles to one another. So we normally have the x-axis, the y-axis, and the z-axis. Or if you like, we have three dimensions in space, up and down, back and forth, and side to side. If you add a time dimension to that, you get four-dimensional
I would
space-time.
tighten this up. Put it right here to use measured systems on 45s and systems when you put the snowflake inside of here.
So I'm going to cheat.
The universe is big. Now, he's trying to make it look tight and doing things, and this is actually one of the models in which you do this. But like I said, you could have tightened this off inside of what this is. The way it does, 2 cell models, Tesla,
Now, if you draw a constant velocity in space-time...
Now, the short on that time dilation system, Hill topology, three-dimensional on multi-matrices that are 0 or 1 through timeline programs, kind of snowflake that. It is, without that factor causally collapsing inside of the factor, it definitely does somehow by keyword search autonomously think GPT-3, but BB.
The further you go. So there's a curve in the
look at some bosses doing some math.
And because gravity causes acceleration, it causes a graph which is curved.
I need them to get to the same place on the math, on timeline, so I'd see something.
That therefore, in some way, space-time must be curved. If it
calls a model. We'll get to one here in a minute when I hit it. It's like that's that grab in the classroom. It's like one of those special ones, sexual fundamental failure behavioral. It's like where you're supposed to be in here for what that visual is. That field theory. The screwball or some kid screwballing around.
And there they are. You may observe that there is only one equation, but in fact that's not true, because you will notice that there are some indices, mu and nu, which arise in several places.
Once we have something in common out here, it's everything. But you want it to be something special. I'm a Mason that builds those things and defends those things over here at the tomb. Defend. It's like you want it to be mu over here. What I cleared off on some of the pipes of this material is that this is wrong.
So
this is just the M0 to M1.
Between 0 and 3. And the combination of mu and nu means that there are 16
same way with the bullet. I mean, you crack the atom inside of here, you light up the mouse traps to double phase that thing down so it releases even more energy or inside of those timelines, increase that production on the floor. That's why the Hadron Collider over at the stone mills. Plenty of them do the exact same math. Singularity, I jump through the wormhole on a graph that hits some number, some skid-steer trick or training model that takes it and changes that index. Mentions in electromagnetism. Doesn't matter, because I'll be like, you couldn't do it. You're taking out one of my generals right now. You're taking out what the value of a differential on these things doesn't graph off on the vector positions for. And then it turns into the carbon index for Bill Gates and the stone mill relative to the corn farm. We'll talk about that one later. We're working this one, which has still got a number.
G mu nu is the metric tensor. We'll derive that. Then we have R, but with no indices. That's called the curvature scalar, and we'll show what that is. Then we've got capital lambda, which turns out to be the cosmological constant, and we'll explain the reason for that. And finally, we've got T mu nu, which is
literally pack it in there. You know, it's like, what's R? R could be anything. Well, they wanted to be close to something. R, Ricci tensor, or whoever. Mu, velocity, or cosmological constant, whatever you want to call this bullshit to be at the time. Make and then you can say when talking to somebody, well, I thought it was something like this, or you already know that, well, alright, whatever, it's a value, I multiply it, I time it, I make sure it's in the snowflake there, about, that's got to be the first step when I home tomorrow morning, every morning, in the operation. Wake up, Mars is here, it'll be here in a couple of days, a little bit more during the year, it'll be...
tells mass how to move. So here's our agenda for the remainder of this video. We've done the introduction. Next, we shall do metric tensors. Then we'll move on to Christoffel symbols, which are capital gamma terms.
Nobody can understand it half the damn time anyways. And even if you come at me, Dark Web, with some shit like this that broke this specifically,
involved in the Ricci curvature tensor, so we'll need the Christoffel symbol. Then we'll look at curvature itself, which will enable us to derive the Ricci curvature tensor.
But I need it,
Bob.
Over there, doesn't mean
then
we'll
look at the stress energy momentum tensor, and then the cosmological constant, and finally we'll put it all together.
Okay.
You may want to take a break through this video just to